So we have started doing number theory with Euclid's GCD algorithm. It has been many days, so let us recall this equation, which is you are given integers a and b, and you are interested in the largest integer which divides both of them. It has to be unique, and we do it by division, right? So you first find the quotient q1, remainder r1, and then do the same thing with b divided by r1, and so on. So there will be k steps, and in the end you will reach 0. When you reach 0 divisor, then you say that you will output the dividend, which is rk. Now based on this algorithm, you immediately get something highly non-trivial, which is that GCD is a linear combination of, integral linear combination of a and b. And so this is the extended Euclid GCD implementation of the algorithm. And we had, as an exercise, you have to show an optimal example where the number of steps is maximized. And we say that for n bits, it will be around 2n steps. Okay, so it grows with the number of bits instead of the value of the number, because the value is exponentially large, it's 2 raised to n. But this algorithm only takes n steps. Right, so it's an incredibly fast algorithm, nothing better can be dreamed. And Bezout identity is also unique in a way, so which is this, that if you want alpha to be less than, okay, so in this case we are looking at the general case. So a and b are integers which share a GCD, this bracket a comma b. So you look at a prime and b prime, right, which is that you remove the GCD. So now a prime and b prime are the co-prime parts. If you want alpha to be smaller than b prime and beta to be smaller than a prime, then they'll be unique. Okay, this is what the statement here is saying. Any questions till now? Okay, so how do you prove this? So first you show that they exist so a prime, b prime are the co-prime parts. Their GCD in particular is 1, and they respectively divide a and b. So by Euclid's GCD, there exist, I'll use the same alpha beta, there exist alpha beta such that alpha a prime plus minus beta b prime is 1. This you can deduce, right? So by Euclid GCD algorithm, extended GCD algorithm, you have this alpha beta. Linear combination has to be the GCD, which in this case is 1. Right? So you can find this alpha and beta, both are positive because of the minus sign. There might be some issue that alpha is negative while beta is positive. You have alpha a prime plus beta, maybe I should do that. Let me assume that a prime is greater. It will not matter. say E prime is bigger than B prime, then there will be these alpha beta positives such that alpha A prime and beta B prime difference is 1. Is this clear? This is just what we have already done, just recalling those steps. And from this you can see that the equation in blue, A comma B GCD equal to alpha A plus beta B, yeah, there is some inconsistency getting added. Let me not use minus at all. So alpha beta are just integers. And now you see that the equation in blue, GCD of A comma B equal to alpha A plus beta B, that is clearly what we have, right? Because you can just multiply this one equation with the GCD of AB and you will get the blue equation. So all that remains is uniqueness. Why is alpha beta unique? So here we can, without loss of generality, you can assume that alpha is less than B prime and beta is in magnitude less than E prime. So in sign it will be this. So this we are assuming because we can use this trick that we had before. Where was the trick? Yeah, this one, the light blue property at the top, right? That alpha A plus beta B, then you can also reduce alpha by, you can add SB here and then on beta you can subtract SA, right? So that is essentially, you can think of it as alpha being divided by B. And the quotient S that you get minus SA you can do on beta. So by doing this repeatedly, you can make sure that alpha is smaller than B prime and beta is smaller than A prime in magnitude. That is what we are doing here by this reduction. Okay, so by that reduction step, you can make alpha and beta sufficiently small. Okay, this is again algorithmic. You can implement this. It's not hard. Just basically you are just dividing. If alpha happens to be bigger than beta prime, B prime, then you can divide. Or if beta in magnitude is bigger than A prime, then you can divide. Okay, and so let me say one of them becomes small for now. And once this is small, beta B prime is then equal to 1 minus alpha A prime in magnitude, which will be smaller than B prime A prime, which implies that beta is also small. Okay, is this clear? So once you have ensured that alpha is small enough, it also implies that beta is small enough. Okay, simultaneously you reduce both. So now the existence part is complete. We have shown that there is alpha and beta such that alpha is small in magnitude, beta is small in magnitude. and the Bezout relation holds. Right? So the only thing that remains is uniqueness. Why is it unique? So suppose it's not unique. So you have GCD, in one way you write it as alpha 1 A plus beta 1 B. In another way you write it as alpha 2 A plus beta 2 B. And the interesting equation you get is this. Okay, and from here can you deduce that alpha beta are unique? What is the magnitude of alpha 1 minus alpha 2? So alpha 1 was strictly smaller than B prime. In fact, alpha 1 you can assume to be positive. So alpha 1 and alpha 2 both are positive, and they are, they are non-negative and strictly less than B prime. So the difference is also less than B prime. Right? And this equation actually is also for A prime, B prime. That's what I want. That's what I want to use. So this means what? So that factor alpha 1 minus alpha 2 is smaller than B prime, and on the RHS you have B prime multiplying. What can you deduce from here? Can you deduce that hence alpha 1 minus alpha 2 is 0? What is the proof of this? That both of these are 0? That needs a proof. Sorry? Alpha 1 minus alpha 2 is divisible by B prime. Yeah, so how do you deduce that from the above equation? Exactly, so actually that requires a lemma. Let's prove that claim first. That so I want to show that A prime, B prime, co-prime, and let me use a different notation here. This is a general claim. So M comma N are co-prime, and M divides something N times alpha. Then it means that M divides alpha. Okay, this is what I want to show. If I show this claim, then in the orange equation, since B prime is co-prime to A prime, then B prime is forced to divide alpha 1 minus alpha 2. But alpha 1 minus alpha 2 is smaller than B prime, so it has to be 0 then. Okay, that is how we will conclude. So from here B prime divides alpha 1 minus alpha 2 A prime, and that red division property together with the fact that alpha 1 minus alpha 2 is quite small, you will get the uniqueness. So okay, how do you prove this claim? this is a very basic property of numbers. How do you show this? Sorry? M does not divide alpha. Yeah, how will that help? No, you have to do something with the product. So these are just individual informations that M is co-prime to N and M divides or not divides alpha. What does it say about the product? Product is a third object, right? So this proof would have been difficult, but since you have seen Euclid GCD, you can use that. You can use the Bezout identity here. So the way you will use it is this Bezout identity implies that you have um plus Vn equal to 1. You have this equation of integers because M and N are co-prime. So you multiply this by alpha. And now you are given that M divides N alpha, right? So this means that M divides alpha. Is that clear? So this is a completely automated proof. Once you have Bezout identity, you don't need to do any further analysis. You just multiply that identity by alpha and use the fact that M is a factor of N alpha and M is already a factor of the first summoned alpha. So then obviously it's a factor of alpha. Is this clear? So this is the, you can call it the claim for cancellation. In a way it is cancelling out N from the game. And using this cancellation lemma, you have deduced that alpha 1 is same as alpha 2 and beta 1 is same as beta 2. So from, you can go back and deduce now that there is no other solution. Alpha beta is unique. Okay, this finishes the proof of this uniqueness of Bezout identity. Any questions with this? Okay. So using similar proof, we can also show a property of factorization of numbers. So which is the fundamental theorem of arithmetic. Which is simply unique factorization. So what does this theorem say about factorization of integers? For all numbers n, what can you say about the factorization into prime numbers? So that first existence property is that n will factor into prime numbers. There exists prime numbers such that n is a product of these with some repetition. So these are distinct primes, right? You can even order them. So there exist distinct primes such that their powers multiply together to give n, and moreover this is unique. Okay, which means that the PIs are unique and the EIs are also unique. Okay, there are unique prime powers which exactly divide n, and their product is n. That's the unique factorization theorem. So this again, although looks very simple, it's not a trivial fact. Certainly it's not trivial to prove, but once you have seen Bezout identity, you can do this again mechanically. Basically, you will just use the cancellation lemma, this claim that we had. You can just use this claim, the cancellation claim. Well, okay, so let's do this in steps. So first is the existence part. So why will these prime numbers exist, right? I mean, any option, why will it exist? We don't care about uniqueness. So what you do is you just start from the smallest prime, which is 2, and you keep dividing as much as possible by 2. When you can't divide, then you move to 3, and so on, right? So just this simple, this trivial algorithm will ultimately give you this RHS. Is that clear? Because, I mean, what is the biggest prime which can divide n? Yeah, I mean, n can itself be prime. So either that happens. If n is not prime, then the biggest prime which can divide is around square root n. Right? So if n is itself prime, then you don't have to do anything. And if it is not prime, then you have to only enumerate primes from 2 to square root n. So base case is either n is prime, then you just have E1 and the exponent E1 is 1, and k is also 1. That's the base case, or n has largest prime less than equal to square root n. Is the square root n part clear? Sorry? Yeah, this claim is not correct actually. Yeah, because you can have 2 times n by 2. Shouldn't use this. Yeah, then it will be n by 2. Yeah. So either n is itself prime or the largest prime it has will be n by 2, because yeah, you can look at the cases. If n is a square, then the largest prime can only be square root n, or in the other extreme, maybe 2 divides it, so you have 2 times n by 2, which can again be prime. So it cannot exceed n by 2, because if it exceeds, then there is nothing else to multiply with to get n. Yeah, so overall you have this, I mean the range is kind of clear for your algorithm. You go from 2 to n by 2, those are your primes, and you divide by each as much as possible, you get the EIs. Yeah, and by the way, EIs I assume to be positive. I don't want it to be 0. and I want P1 to be at least 2. Yeah, so as much as you can divide Pi, you will get Ei to be 1 or more, and after that you will move to the next prime and so on. So a subset of these n by 2 up to n by 2 primes will be P1 to Pk, okay, of interest. So that clears up existence. So this gives you n equal to product of Pi Ei. Is this part clear? Yes, so it's almost a formal proof. You have this algorithm to factorize n completely into prime numbers. Basically, you at no point, in the end, you cannot end up with a composite, because if it's composite, it will again factor, right? So just by the definition of composite or prime, you get to this prime powers and factorization. So the second part is the trickier part, which is uniqueness. Why is it unique? So here, suppose it is not. So let's continue using this shorthand. So Pi Ei is equal to Qj Fj. Okay, and suppose there is some difference in either Pi Qj or Ei Fj. So what happens? What do you get from here? So you keep using the cancellation claim that we proved before. So you see that Pi or say P1 has to be one of the Qj's. In fact, it has to be Q1. We are using sorted primes. So P1 has to divide one of these Qj's, and since primes are, if they are distinct, they are obviously co-prime. So it means that Q1 has to be P1. So from that you deduce that P1 is Q1. And what do you deduce about E1 and F1? Same argument, right? You basically, if P1 is Q1, then you can remove P1 to the E1 from both sides, and nothing should remain for P1. So which can only happen if F1 was E1. Right, and then you continue doing this, so you will end up with whatever is the bound. So say here you were doing I1 to L, K, and here it was J1 to L. So you will deduce PL equal to QL and EL equal to FL, which implies uniqueness of factors. Is this clear? Any questions at this point? Right, so you know that prime factorization of numbers is unique. So that is the fundamental theorem of arithmetic. And this is not a given, so we will, when we do more algebra towards the end of the course, we will see that there can be situations when mathematical objects don't have this property. Okay, factorization can be defined in a different way when this will be violated. So the reason why it works here is quite fundamental. Okay, so essentially based on this observation, we can study numbers via factors and via primes. And prime powers. Right, this is because a number has a unique signature into primes or their powers. So usually what happens is when you want to study number properties, you will study it via its prime factors. So that takes us to modular arithmetic. So most of the time we will avoid studying composite numbers and we'll just study prime numbers, because primes are the building blocks in this sense of all numbers. Okay, so are you aware of this modular arithmetic? What is that? What is the term modular for numbers? Not to be confused with modular forms if you are too advanced in math. This is something trivial. So modular just means that you want to look at the remainders, or for this n and for some prime p, you want to look at n divided by p. Okay, what is the remainder? You want to study the properties via studying the remainders by dividing by other numbers, which are usually smaller numbers. So this is kind of a silly attempt to do recursion. Okay, you have a big number, so you divide it by something smaller, so you get a smaller number. Okay, it's kind of a attempt to recurse, but it is very, very successful, as we will see. So some examples are, suppose a year starts by a Sunday. So what is the 184th day? Right, so some students may want to list days from 1 to 184 in a long notebook. That's also allowed, but then a smarter way will be that you observe that when does Sunday repeat, right? So you look at the period. So the answer would be, sorry? So you basically divide 184 by 7. Right, and then it will reduce to a number between 0 to 6, and then you can guess. Sorry? Yeah, so you do that. At least it's better than enumerating the whole year. So this is a much smarter way to attack these problems. So this is like, think of this as mod 7. Okay, whatever that means, and it basically means that you want to divide by 7 and look at the remainder, because you know that what is important is just the remainder, whether it's 0 or 1 or 6, right? So there is still enumeration, but now the enumeration is only on 7 days, 7 numbers instead of 184, right? So that is what will always happen in such problems. And soon it will become crazy, because somebody may then ask you questions like, what is the last digit of 2 raised to 64, right? So now this is a number which is very, very large. So actually computing this and storing this and I mean, it may be 2 raised to 640 also, which will be just impossible to store, right? So you cannot really compute these digits and store it anywhere. There is not enough time in the word, and also there won't be enough space. So thankfully for you, these questions actually don't require any other digit except the last digit. So which can be obtained by remainder by 10, right? So this is kind of a mod 10 question. So again you have to calculate, but you have to calculate only up to 0 to 9 and not anymore, right? So you can do this in a very systematic way, which we will see later. So let me make it slightly bigger, and then it is impossible to store. Maybe that is not correct. Let's make it crazier. Something like this or this. So then it will be definitely impossible to store. Yeah, but still, whatever it is, it's still just mod 10 arithmetic. So as long as you have some compact representation, like we have, right? I mean, this huge number we are able to still write in one place on the slide. So it means that there is a compact representation. So once you have a compact representation, then you can use mod 10 arithmetic to still find the last digit. You don't need to compute the whole thing. So this is an incredibly smart way to work with large numbers. But we can work with numbers 0 to 9. And that is what we will try to store. What are the last digits we are getting of the intermediate numbers that we compute here? So we store only one digit. So then, motivated by that, we can define R of n let's say R of n d, or we can suppress this. So this is the remainder n% d. So n divided by d, remainder. Okay, so n divide n by d, and then whatever is the remainder, that is what this function gives you. So for example, here you are interested in the remainder of n when you divide by 10. Where n is this large number. So the reason why this function is of interest everywhere in math and now especially in computer science is because it has this interesting property that remainder of A times B is, how is it related to remainder of A and remainder of B? Is the product, right? Irrespective of what D is and what AB are. Not sure whether we have to prove this. Is this identity clear? That is true. So the remainder of AB, A times B does not change if we first take the remainder of A and take the remainder of B, multiply and then take the remainder. Right? How do you show this? So, I mean, this division algorithm that we used in Euclid method, what was happening there? So, remainder of A is, you will write it as D times some quotient plus remainder. Sorry. Let's, yeah. So, write A as D times quotient plus remainder, and you will write B as other quotient remainder, and AB as this, right? So when you do division independently 3 times, these are the equations, but then you observe that, and this must have been a non-trivial observation 300 years ago, that when you multiply these 2 equations, left hand side you will get AB, which matches the third equation, and on the right hand side you will get D times something plus product of the remainder. So you will get D times something plus the product of RDA and RB. Right, and so that is now equal to the RHS of the third equation. From there you will deduce that, well, I can as well multiply the remainders and then again divide by D, and I'll get equal things because my representation is 0 to D minus 1 of remainders. Right, so these things, these are all whatever remainder you look at, it's between 0 to D minus 1. Okay, so whatever you will get from the third equation, the number, the remainder 0 to D minus 1, you can as well get it by multiplying the 2 remainders and dividing by D. Okay, so that is what the top equation is expressing. Is this clear? Okay, so if this is clear, then we are ready to define modular arithmetic properly so that we can use it. The problem with this equation is that it has RD appearing 4 times, right? So we don't want to use such equations. It's too complicated to write. So what this great guy Gauss did was simplified the notation so that we can use it intuitively. So the definition of Gauss was that you write A equal to B mod n if n divides A minus B. Okay, so that is the notation. So to read the first equation again, this the first equation is basically saying that I mean, in a sense, it is this notation removes the remainder operator. Okay, you don't have to keep worrying about the remainder. all you have to worry is that, I mean, you can now talk about equations, and you can say that two numbers I consider equal if they have the same remainder. So A times B's remainder will be the same as the remainder of A times the remainder of B, okay, without keeping track of these exact remainder operators. So, so it basically divides, more importantly, this mod relationship. It's basically a relationship between integers. Once you are given n, then for all numbers a, b, the relationship is the following: a and b are related if they have the same remainder when divided by n. Since I'm using equality, you have to show that it's an equivalence relation. Is it? Yeah, so that is what is needed for the this thing to be well defined. So mod n is an equivalence relation on integers. Okay, so it's equivalence relation because it is symmetric, of course, and it is reflexive, again trivially, and it is transitive as well. Right? If AB have the same remainder, then and BC have the same remainder, then AC have, of course, the same remainder. So because of that, this can be thought of as a new equality. But the equality will depend on the number n that you fix. Right? So there are now many ways to define equality on integers. Infinitely many ways. Okay, so just as an example, how far is this equality from the actual equality? For integers a, b, when will you be able to deduce that a equal to b mod n implies a equal to b? Is it ever possible? When? So the converse is obviously true. Right, the converse is true, but what about the forward direction? How far is it? Yeah, if n is, yeah, if a and b are smaller in magnitude, then you can reduce. So no, let me first write this down. If the magnitude of AB is less than n, then is it clear that you deduce A equal to B? Yeah, that's all. So if AB is sufficiently small, I mean, or like conversely, if n is sufficiently large, in that case, this is not a new notion of equality. But remember that our goal is to do this stupid recursion on numbers, right? We want to reduce big numbers to small numbers. So n will always be quite small. So in that case, there will be no forward direction. You cannot deduce A equal to B, but still you can do useful things. Yes? Sorry? Yeah, this definition is for all integers. Exactly. Yeah, we want to do that in many cases. But then it will create a problem here, you are saying. Should I say A equal to plus minus B then? No. Yeah, no. So this will need, then, okay, the purpose of this example was not that. So let's just keep it positive. If AB, yeah, so I think for now we just take it positive. Let's just keep this example. Let's not worry about the negative part. No, here just if you think about non-negative A and B, then in that case, if n is sufficiently big, you can deduce equality. I mean, the negative case you can study separately. Let's not mix them up. The definition is for any AB in Z. So positive or negative. Right, so let's see an example of this, how this drastically changes the calculations. So suppose you want to compute R of 2 raised to 64 dividing by 10. Right, suppose you want to compute the last digit of 2 raised to 64. So how will this thing help? Mod 10 arithmetic. So first you write 2 raised to 8. What is the value of this in smallest terms? Right, what is the digit of 2 raised to 8? That's clearly 6. And then you use the multiplicative property. So you can square this. So you'll get 2 raised to 8 whole square is 36, which is again 6. Maybe I should not use this equal sign. It could get confusing later. Let's just use this other sign which I like better. Okay, this A congruent to B mod n, to distinguish it from equal. So for example, here we mean this thing. 2 raised to 8 is the same as 6, and then 2 raised to 8 whole square is the same as 36, which is the same as, 6. Which is the same as 6, and so now you can see what is happening. So after similar things, you will reach 2 raised to 64 is also the same as 6. Right, so and if you keep doing this infinitely many times, you will reach 2 raised to n is also 6, right? So this is true for all n. So for all n bigger than 2, why do I need 2? Yeah, greater than or equal to 2. It's only n equal to 1 where you get 4. Yeah, after n greater than 1, in all cases 2 raised to n is 6. Right? So in particular 2 raised to 100, which is impossible to store, that digit also you have calculated, the last digit. Right? So the things become highly systematic by using this mod arithmetic or modular arithmetic, mod 10. Right, and the notation is very simple. You don't have to worry about this R10 bracket notation. Is this clear? So this notation is due to Gauss. in 1800s. Okay, so this is a very useful notation. Almost everything in number theory or algebra assumes this. Okay, and so what this means is that 6 mod 10 is not just a number, it actually represents infinitely many numbers. Right, so it is what is called a residue class. So let's first write this simple property that if A is congruent to B mod n, then as we have seen, there exists a K such that A is equal to B plus Kn, right? And it's if and only if. So any number like B plus Kn, which is an arithmetic progression, if B and n you fix, then this is an arithmetic progression. So the whole arithmetic progression is being represented by B mod n. Right? So B mod n is actually, you can think of it as a set. You can think about it as a number B, but also it represents a set of numbers given by B plus Kn, which is also an AP with common difference n and starting an offset B. So this motivates the definition of residue class. So B plus Kn go over all K. This is the residue class of B mod n. And how many residue classes are there? There are n residue classes, right? So you can change B from 0 to n minus 1. These are the n residue classes whose union is everything. Right? Since, I mean, it was bound to happen because we have an equivalence relation. So equivalence relation will partition Z into classes, so it's that class. So we can write that as a property. So Z, so okay, for all n, Z partitions into n residue classes. N residue classes mod n. So instead of looking at this set, which is an infinite set, we'll just call it B, right? B is the representative. We'll just take this small number B as the thing of interest for in calculations. So in fact, we'll define it they are 0 to 1 to n minus 1, and we call it Z mod n. Okay, so we'll, instead of now working with the infinite set of infinite integers, infinitely many integers, we'll just work with 0, 1, dot, dot, n minus 1. We are calling it this fancy notation z slash n to emphasize that the arithmetic is modern. Okay, if the arithmetic is not specified, then this is just a finite set. It will not represent everything. So it represents everything only because we are doing modern. Okay, that is why actually each element is a class and not just a number. So when we say z slash n, we'll mean everything I have said. Okay, that is what this fancy notation will signify, that it's z slash n arithmetic. Okay, we'll continue next time.